Today I'm going to talk about a series of projects we've been working on this idea of language modeling from pixels. And I have a disclaimer, which is that in the final part of the talk, there will be some examples of text that are racist in nature. I'll give another warning before those appear at the end. I lost the internet connection on my laptop just in time to start, so let's see how well this goes. Since you're here, you probably already know that language models are statistical models of text that we can use to estimate the probability of a string. And if we go all the way back to Shannon, we know that this is intractable for most strings, but that if we use some simplifying assumptions, for example, a bigram Markov chain, then we can estimate this using the data that we observe. Things have moved on a bit since 1948, and now we're using language models everywhere in our daily lives. We use them in spelling and grammar checking, in machine translation, web search, text prediction, chatbots, code support tools. It's everywhere. And the current status in the field, I think, can be summarized as scale. This is it. If you look at the graph on the left-hand side here, we go from 2018 to 2023, and the y-axis is the number of model parameters. There's a pretty clear trend within NLP researchers. The scale also buys us some interesting properties like emergent abilities, as shown in this plot on the right-hand side from Wei and colleagues in TMLR 2022. As you scale up the number of parameters in the model, some tasks become possible in a zero-shot setting. So what's left? If NLP is only about scale, why should we continue working on it? I believe that NLP will be most useful when it works for all written languages. There are about 3,000 written languages in the world, and there's at least 400 languages with more than 1 million speakers. And NLP typically only covers 100 languages in most of the models that people use, which gives a lack of technological inclusion for billions of people. The plot here on maybe your left, on the left, shows on the x-axis, the number of speakers in a language. So we can see here, if you speak Mandarin or English with billions of speakers, you can expect high-quality language processing tools. If you speak a language like Turkish, which has complex agglutinative morphology, it's much more challenging. I don't know the situation for Polish NLP. I know you have about 40 to 45 million speakers, so it should be a reasonably high-quality language. Is this the case? So-so, it's getting better. If we go further down the scale to Danish, which is where I'm currently working, NLP could be a lot better. And that's still not yet at this 1 million speakers mark. We can go further down to Basque or Faroese, and things just get much worse. And so the main question that we're trying to address is how can we create high-quality language processing technologies for all written languages, not just a privileged set of 100. So to recap things that I think you already know, NLP is a pipeline. So we typically start with a piece of text, like this statement about Søren Kierkegaard. We normalize the text. That usually involves splitting out the punctuation. After this, we'll tokenize it using some kind of pre-estimated tokenizer. If you have a really bad tokenizer for Danish, you might split Kierkegaard into multiple units. If you had a good tokenizer, this would be such a common word. All the other words, we're just going to tokenize them as normal. After this, each token is associated with a real valued vector, and these vectors are the input to a large neural network, for example, BERT, XLM Roberta, GPT, or Llama. And then we do some kind of syntactic or semantic analysis on top of that, or maybe some zero-shot prompting. So what's the problem? It's that NLP is actually an open vocabulary task, and the ability of a model to process unseen words is directly related to its vocabulary. There are two typical approaches to addressing this. One is to train a tokenizer over a corpus, for example, using byte pair encoding. Here, unseen tokens are usually not in the vocabulary unless you include a byte level backoff. Or there's a corpus-independent approach using something like characters or bytes in which we increase sequence lengths. And this is manifested in modern implementations of these models in two places where we get a bottleneck. In the bottom, at the input layer, we have a representational bottleneck in the embedding. In other words, we just cannot represent the tokens we need to represent. We also have a bottleneck at the output layer, which I call a computational bottleneck. If your model has 5 million words in its vocabulary, it's quite expensive to calculate the softmax normalization when you're trying to predict words or to train your model. So where's the sweet spot on this axis? If we go from the top here, we have long sequence lengths. This is when we represent language as bytes, as example in byte T5, or characters in Canine or Carformer. We can also think about models with things like small subword vocabularies, like BERT, or maybe Roberta has a bit more in its vocabulary for subwords. We go all the way down to the other end of the scale, and we have full word coverage. To the best of my knowledge, nobody actually does this. The only example I can find is Word2Vec from 2013, where the embedding vocabulary is 3 million words. And this is just not something that people do in modern natural language processing models. And so today, I'm going to talk to you about treating language processing as visual processing. That's the main argument I'm going to make. So we're going to take this pipeline that I explained at the start, and we're going to throw everything away. And we're going to replace it with one step, which is to render text into an image instead of treating it as a set of tokens. So what that means is if we take this Amharic sentence, which says Ethiopia is a country in East Africa, we are going to render this into a canvas, like what you see here. And then when we pre-train our model, we're going to randomly mask some parts of it and train the model to reconstruct the missing parts at the pixel level. This model does not explicitly know anything about words in its input or in its output. But I'm going to try and convince you that it can actually learn language representations that transfer across languages. So the remainder of today's talk is going to be split into 3 parts. First of all, I'll explain the model that we've built, and then I will critique the model that we've built and tell you that we did it all wrong. And then I'm going to finish with this part on how we can apply the model to other contexts, for example, working with historical documents. I have no idea how much time I've used so far because all my technology broke, but I think we're going to be on schedule. So now I'm getting an echo. Do you get an echo? No? Okay, I'll just hear myself 3 times. So the first part is going to be based on a project we call Language Modeling with Pixels. This was a really exciting collaboration with people from the University of Copenhagen, Johns Hopkins University, and KU Leuven. So the model that we have built takes text in its input. For example, you see here at the bottom, there's a small cylinder with a collection of documents. We grab a sentence out of this. For example, my cat enjoys eating warm oatmeal for lunch and dinner. And we render this text into an image. We use the Pango Cairo renderer, which is fully open source. We use the Google Noto font library, which is also fully open source. And we render this into 16 by 16 pixel patches in a continuous fashion from left to right until we reach the end of the input we want to render. Then we have a convolution projection layer, and we add in a position embedding for each patch. We add in a special classifier embedding token, and then we mask spans in the patch space. So the inputs you see here that are marked with kind of dashed boxes, those are not inputs to the model, at least to the encoder layer. But it sees everything else. Then we have a 12-layer transformer encoder that processes the patches that are not masked. This gives us a set of encoder embeddings, and then we input some identifiers for the parts that need to be reconstructed. This goes through an 8-layer transformer decoder, and the model is trained to reconstruct the pixels that it did not observe, only in the masked regions from the input. That's it. That's the end of the talk. This is enough to learn a language model. What we actually do is a bit more complicated. So we have a flexible text renderer that can support emoji in full RGB space if you need to. We haven't used this yet, but it's probably going to be useful for working with social media text in the future. We can also support left to right and right to left and logosyllabic writing systems, even within the same inputs. Here I'm showing examples in Arabic and in traditional Chinese. And we can also support word-level rendering, where perhaps for a downstream task, you want to know the exact location of each word. Our renderer works at the glyph level, and we can control exactly where things are drawn. The rendered text is also quite compact. So you may have been thinking already, this is going to produce really long sequences, but it doesn't. It produces sequence lengths that are at least as long as the BERT language model. So this plot I'm showing you here is text from the Universal Dependencies dataset, which is a large-scale collaborative effort to annotate parts of speech and dependency of relations between words. There are human reference segmentations in here about where boundaries are between words. And we can see here for Turkish, the proportion of the text that uses, what would that be, like 8 to 10 words, is really peaked for the reference. We also compare other models here, like BERT, or MBERT as its tokenizer, or Pixel, which is shown in the dashed pink line. So as you can see, you don't really pay a penalty for using the Pixel model to encode this as patches. Unlike some large language models, there's recently been a claim that if you work with a lower resource language, you will typically pay higher API access fees because there's bad tokenization of those languages. And this doesn't just apply to Turkish. These plots are now for 9 different languages. So for Arabic, Pixel is really compact in terms of its encoding. It can actually encode more characters within patches than the reference segmentations. You can also see how it looks for English or maybe Japanese or Finnish. There's one particular thing I'd like to highlight here. For Korean, the BERT language model tokenizer is able to do a really good job of matching the reference length because most of the tokens are UNC. So it's kind of cheating. But overall, very compact rendering. In terms of how the embedding layer works, like I said, we render into a canvas, and then we have this convolution layer. So what happens here is we take our rendered text, which is 16 by 16 pixel in RGB space, and we convolve this with 768 kernels, each of which is also 16 by 16 by 3. And this gives us a single 768 dimensional embedding. And you can think of these kernels as taking snapshots of the input patch. Instead of looking over sliding windows within it, each of them takes a snapshot. And this happens simultaneously for all of the inputs in the input layer, in the input sequence. And that gives us these embedded representations. We can also try to imagine that the convolution kernels are learning something that means something to us as humans. This is, you may not believe it, it's actually an animation showing how the convolution weights evolve during pre-training from step 10,000 to step 1 million in intervals of 10,000. So what can I try and convince you happen here. Some kernels seem to learn exclusively about the presence or absence of pixels in an input patch. Either they're entirely yellow, which means they're fully activated, or they're entirely dark blue, which means there's no activation. Many of these kernels seem to capture horizontal strokes in the patch space. I don't really know what that means. If you think you know, please come and speak to me afterwards. And a few of these kernels capture curved shapes. And this is probably because we do an uncontrolled rendering where letters appear across patch boundaries. And maybe you can see this. You can see a kind of curved shapes in these regions I'm highlighting here in black. If you can't see it, then yeah, I had to look for a long time to see these things myself. So those are the convolution kernels and what they may or may not be learning. I'm also going to talk to you a little bit about the pixel reconstruction. So I said before that we have our output embeddings from our encoder, then we insert these position embeddings in the decoder for where we're going to reconstruct. Everything goes through an 8-layer transformer, and then we have a linear projection into the 16 by 16 by RGB pixel space. So what that means is there's no softmax normalization here. There is no large vocabulary at all to process this over. It just doesn't exist. And our loss here is just the mean squared error between the patch that should have been produced and the patch that was actually predicted by the model. And we do this over all of the patches that are masked. And what we get out of this, before I start telling you about some of the experiments we ran, is a new type of generative model of language. Here, I'm showing you examples of pixel reconstructions at different steps during the pre-training process, going from 100,000 steps to 1 million steps. And this is an article about how penguins are streamlined and how their knees are positioned. It has never seen this document. So I'd like to highlight how some good things that we can see here. At the top, we can see that at 100,000 steps, the model is doing a really bad job of reconstructing what's happening within this. It doesn't really know how to produce having long legs. But by 1 million steps, it can reconstruct this nice and cleanly. And the second example, at 500,000 steps, the model invents a word that doesn't exist. It invents the word clusion. This is not a word in the English language. You can look this up in any dictionary. It just doesn't exist. But by 1 million steps, it corrects itself, and it realizes that the correct missing prediction is illusion. It's not all good. Sometimes, no matter how much pre-training, the model just cannot reproduce text accurately. There's too much uncertainty. And maybe as you look through this, you can also see some of these uncertainties where the model is trying to predict 2 characters in the same space. That's just a general property of how the model's trained and how we can use it. To convince you that I didn't cherry-pick these results, I also have the text of the web page for this conference. I am absolutely sure the model has never seen this, and I just copied it in, and it's actually quite good at reconstructing the announcement. The biggest problem is that it thinks the Copernicus Science Center is in Washington instead of Warsaw. I don't know why it thinks this. Maybe it hasn't seen anything about the Copernicus Science Center during its pre-training, and it sees a gap where it can fit in the word Washington. But apart from that, most of the reconstructions are quite nice, and it understands the topic of the conference, even though it hasn't been pre-trained on machine learning conference announcements and web pages. And when we want to adapt this to downstream tasks, we throw away the decoder, and then we just do what people have been doing for a very long time, and we create task-specific fine-tuning classifiers. So if we want to do part-of-speech tagging, we attach classifiers to all of the outputs. If we want to do sentence classification, we attach a classifier to the CLS token. It's quite straightforward. In terms of how we pre-train this model, we only pre-train on English data. This is the English Wikipedia and the English books corpus. We pre-trained it for 8 days on 8 A100s. We recently managed to get this down to 2 days on 8 A100s by doing some optimizations to how it's pre-trained. And our model is quite compact. It has 86 million parameters in the encoder and 26 million in the decoder, and then later we throw away the decoder. There is a small amount of non-English text in our pre-training data, about 0.05%. And the type of text it would be is like these examples here, where in the article for the Great Wall of China, it explains how you would write this in traditional or simplified Chinese. And I would argue that that is not enough to claim that the model is learning Chinese during pre-training. It sees so few pixels related to this. In terms of the downstream tasks that we evaluate this on, we really focus on tasks that require multilingual capabilities. Overall, we evaluate it on 32 languages in 14 different writing scripts. Very few of those are Latin script. Most of them are things like Devanagari or CJK Han script or Amharic or Arabic or Cyrillic. It's just like everything that's really not Latin. And the models we compare against are BERT-based and Canine-C. And I know that there are more recent models than these, and you're probably using these on a daily basis. But we chose these because BERT-based has a similar pre-training setup in terms of the amount of data, and Canine is a model from Google Research that tries to solve the same problem using UTF-32 code points instead of using pixels. So in terms of the results, the first result I want to present is on dependency parsing. This is, for those of you who are not familiar, it's a task where you want to predict the relationship between words in a sentence. And I'm showing an example up here. So you want to predict that flight is a direct object of the word prefer. And here we're showing F1 over a collection of 10 different languages. And what I'd like to highlight to you is the large gaps in performance you can see between BERT, which is pre-trained on the same data, and Pixel. And it's no coincidence here that when BERT produces unknown tokens in its tokenizer, Pixel vastly outperforms it. We see this for Coptic, Korean, Tamil, and traditional Chinese. And it performs almost the same on English, which shows that it has the representational capacity to learn in this high-resource Latin script language. We also apply this to a task of named entity recognition in several African languages. An example of the type of task we're working on is shown here, where we have this sentence, and the aim is to predict these different named entities. So we can see that for the one non-Latin script language, which is Amharic, that Pixel outperforms BERT, and it also outperforms Canine, even though Canine was pre-trained on multilingual data. And overall, Pixel outperforms Canine on almost all of the languages in this setup. Once again, only pre-trained on English text, and then fine-tuned on each of these languages when we want to transfer that. So I think this is another demonstration of the fact that we can learn these general purpose representations just from English data and transfer it across to other languages through pixels. We have some not so promising results in sentence level understanding in the popular GLUE benchmark. And so here, BERT outperforms Pixel on these English sentence level tasks. It's quite consistent. There's not a single task where Pixel outperforms BERT. And this is something that caused us a great deal of frustration. It's not really clear why the pixel reconstruction objective does not lead to good sentence-level representations, but it's something we've continued to work on since we started working in this direction. We can also ask ourselves, how well would this model deal with adversarial orthographic attacks? This is the type of thing that you probably see in your email inbox. Now, they put in all these crazy characters, and spam filters have to try and deal with this. So this is a collection of orthographic attacks from the 0 benchmark. Starting out from the original example here, which is none, we can have a set of confusable characters. So you can see maybe there's a pi symbol, or there's the E from the exponential symbol. We can also have attacks where we shuffle the interiors of words, preserving the first and last character. We can shuffle the entire word. We can disembowel all of the words so that it's just consonants. We can intrude completely random characters into this to create nonsense. There's also plausible keyboard typos, natural noise, truncations of the text, removing all segmentation, just treating it as a complete string, no spaces, and also a phonetic attack where the word is rendered as you would express it using IPA phonemes. And so there are lots of plots here. The ones in yellow are BERT, and the ones in blue are Pixel. And first of all, I'd like to draw your attention to this confusable attack. So here we're getting these like pi symbols and all these weird things. And the performance of BERT degrades really quickly here. On the x-axis, we have the number of tokens that are attacked in the input. So on the left-hand side, we have no attack at all, and on the right-hand side, 80% of the text is corrupted. Here, yeah, BERT really plummets, whereas Pixel degrades a bit more gracefully. At 80% attack, it still has 60% accuracy on this natural language inference task. And we can look through some of the others, like disembowel, there's not too much difference. Shuffling the words, Pixel is quite robust to this. I'd also like to highlight this phonetic attack down here. So we can see that BERT quite quickly loses performance when it's faced with these phonetic representations instead of the standard written representations. Whereas Pixel is quite robust, it's able to learn this from the input data, which I think is also, once again, a nice demonstration of the performance you can get from pixels instead of tokens. And to me, it's quite natural that the main problem here is that when you have these orthographic attacks with a pre-trained tokenizer, you end up creating really weird inputs to the language model that don't have much regularity. I think if we go back here, you can see, for example, with the, honestly, any of them, the intrude or the shuffle fool, these create sequences of characters that are going to be very hard to tokenize, and they might actually just end up being character-level sequences instead of something that looks like words or subwords. Whereas the shuffle fool and the original would take exactly the same amount of input space in Pixel. There would be no penalty to pay there. We can also do something a little bit silly and crazy, which is to try to adapt this to new fonts. Our model was pre-trained using the Google Noto sans serif. So it's natural to ask, how robust is this? We tried transferring this to serif-based fonts, and it works quite well. And we also tried something really silly, which was to give it dingbats instead of Latin characters. It does suffer a little bit when we use dingbats, but who doesn't struggle to read dingbats? I know that I can't understand any of this. It's like wine glass, piece of cake, world globe, and bed. I don't know. And I think this is of crucial importance when we want to process new scripts, for example, handwritten text or pre-scanned data. So the summary for the first part of this talk is that I've tried to argue that Pixel is a language model that can just process anything that can be rendered into an image. It has open vocabulary support out of the box. It supports almost every written language that we can render, and Google Noto has support for 140 different writing systems. And this gives us this great flexibility to process written language in many different forms, for example, PDFs or scanned newspapers, and I'm going to come back to that at the end of the talk. So that's part one. In part two, I'm going to tell you about how we did everything wrong. So the text renderer that I spent a long time discussing is flawed, and we tried to revisit this. I know this is like learning about chemistry in high school, where every year you learn that it's actually more complex than you thought. So our text renderer is terribly wasteful, and that's because we render the text continuously. We don't place any control or restrictions on how it's drawn. And here I'm showing you the most frequent patches in our pre-training data. And you can probably see what's in common with all of them. And they're the same word. It's just slight variations on where they were rendered in the input. And that's almost certainly representational and computationally wasteful, since our convolution layer needs to learn that these are basically the same input. And the question here is, can we do better? The answer is yes, we can do much better. We explored this idea of alternative text renderers. So if the continuous one is the one I've just shown you, we can imagine maybe rendering using bigrams. So each patch has a set of character bigrams rendered into it. And they start in their own unique patches. And this way, we can build something like a vocabulary inventory. I'm not going to call it a tokenization because it's completely continuous, but we'll call it an inventory and leave it there. We could also imagine doing structured rendering using maybe monospaced fonts. This is not optimal because not all languages have support for monospaced font rendering, but it does also produce this kind of patch inventory. And the final approach we could consider here would be structured rendering with words, where each word starts in its own patch, regardless of how long the word is. The problem with the fourth option is that it won't work well when we have things like CJK languages, where there is no white space delineation between it. It's actually not general. Whereas something like structured rendering based on bigrams is pretty general. We don't need to know where the words are. We just render bigrams until we continue. And we can see that this would have a real difference on the input representations. So what I'm showing here on the x-axis is the number of sentences observed. And on the y-axis is the number of unique patches. And indeed, continuous rendering is terrible. It produces 250,000 unique patches across 10,000 sentences. So basically everything is unique and never observed more than once. With the dotted dashed blue line, we see with word-based rendering, we get it down to about 50,000. And with either the bigram or the monospace rendering, it's down to just about 1,000 unique patches, which is more representationally efficient. And I'm going to tell you more about the performance of using bigram rendering. We train the model, and I should have said that. We train this model using exactly the same setup as before. Nothing else changes except for how we render the text. That's it. And when we transfer this onto the same set of tasks, it produces much better models than continuous rendering. So the light blue bar here for pixel bigrams is this model. We get improvements over all of our previous results, and for most of these, we now nearly match the performance of BERT when we're pre-trained on exactly the same data. And our performance on the only non-Latin script, and Amharic, reaches 50 F1, which is really a nice result given that it's the only odd one out non-Latin script in this set. We can also go back to the GLUE benchmark. Once again, bigram rendering increases performance again. So it seems that this structural regularity in the input space is very important for sentence-level tasks, especially for things like COLA, where we get a massive boost in performance. We're not quite at the level of BERT, but we're getting there. And we can also do something really counterintuitive, which is we can scale down instead of scaling up. And the better text rendering you get with bigram models allows us to create effective models at smaller scales. So here I'm showing you the average score for the 3 different tasks I've spoken about throughout all of this talk. For language parsing, for sentence-level processing in GLUE, and for tie-dye QA. Here, the light blue on the right-hand side, this is pixel-based. And then in the orange one here, we have the bigrams model also at the base size. And we can also train a small model, which is shown in dark blue, or even a tiny model in light blue, with as few as 5 million learnable parameters. Once you get down to 5 million, you do sacrifice some performance. There's probably not enough representational capacity when you train that from scratch. But I think for me, this is super exciting. We can train these compact models, and at least 22 million parameters, you don't pay much penalty in performance compared to having 86 million parameters. And so the summary of this second part of the talk is that this really simple modification to text rendering can have a big impact on model performance, especially in things like sentence-level processing or named entity recognition. And we can also use this to train smaller scale models, which I think is really useful for people that want to work in low compute environments, and even people who want to maybe deploy this and use it on their laptops. I think that at 5 million parameters, this is actually possible as compared to using some kind of LLM with billions of parameters. The final part of this talk is an application of these models to something that's not dependency parsing or named entity recognition. This is a collaboration with some people at the University of Copenhagen on working with historical documents. And there will be some samples in this that are racist in nature, and I apologize. The last 10 years have seen enormous efforts to digitize historical documents so that historians and scholars can have access to this huge wealth of information that's typically stored away in libraries where you have to go there in person and access the material individually, hand by hand. And a typical pipeline for this digital access is to, first of all, scan these documents into high-quality digital formats, and then to either perform OCR on those or to do something like a handwritten transcription. The OCR is noisy and one-off. The handwritten transcription is very expensive in terms of time and expertise. And then historians will typically search through these documents using text queries to find what they need. And the question we wanted to ask here is, what if we could do this without using any OCR? What would this enable, and is this even possible? We worked with a collection of newspapers from the Caribbean from 1718 to 1876. And this is a collaboration with researchers that are interested in tracking newspaper notices about escaped slaves. In particular, they're interested in finding out the given name of the escaped slave, the reward that would be offered for their return, and the contact person, amongst other questions. And they have a data set of 1.65 million scanned pages with respect to Caribbean newspapers, and the same number of pages for just general newspaper text. And so the researchers in this project designed something that they call Pixel for Historical Documents. And this is a process where we have some historical document-aware pre-training, where we have a mixture of real scanned newspapers and synthetic newspaper-like text that is generated from the Wikipedia and book corpus datasets. All of the data is scaled into a 368 squared image with 16 by 16 patches as throughout the whole of this presentation. And here are some examples of these newspaper-like texts. So you can see that there's a mixture of fonts, there's a mixture of orientations, there's even some noise that's been added into the input to make it look more like that. The actual process for creating this is starting with a 368 by 368 canvas and a data set on disk. They render a paragraph into the canvas. And when they want to keep rendering, they decide, is there more space within the canvas for this? If yes, let's go. We don't also use the same font. We render with many different fonts because this is what you would see in a newspaper. So you can see here we have 3 different fonts. We have different font sizes, different orientations, and then we also add salt and pepper noise and also blotches to simulate this idea that there's bleed through from the other side of the page, which is really common if you've worked with historical documents. And the model is pre-trained on both of these sources of data. We can look here at some of the reconstructions, going from best to absolute worst. On the left-hand side, so the images here, these black boxes show where the model has to reconstruct. On the left-hand side, the reconstructions, I think they're really good. I'm really impressed by how well it can reconstruct some of these texts, like to the editor of the reporter in the middle of the left-hand side. It's really clear at reconstructing this. In the middle, it's also quite clear at reconstructing the different types of fonts it needs to observe within a single page and how these change. Unfortunately, on the right-hand side, it doesn't know how to reconstruct anything. It just produces blurs. So our reconstruction pre-training process is not ideal in this setting. And how do we frame this for the task we're interested in? We look at this as a visual question answering task. So given a canvas, we render the question into the canvas. For example, how much reward is offered? And then we render the newspaper clipping in question into the canvas, which you can see here. And the quality of this is actually much worse than any of the examples that I've shown you from our synthetic process. And we also annotate the context of the answer because there is some gold standard training data. It's shown here with the gray box that the reward was 3 guineas. And then we train the model to predict the label of the answer in this case. The visualizations show that the model actually seems to do what we would like it to do. The black box here is showing where the answer should be located. And the intensity of the redness shows the self-attention in the model with respect to the predicted answer. So we can see on the first example, the model focuses all of its attention into the area which says that the other reward is that you will be handsomely rewarded. In the second example, the question here is what is the ethnicity of the person, and the model is paying most of its attention into this box, but not across the whole answer. So at least it knows where the answer is. And in the final one, the contact person is listed at the start of the advertisement notice, whereas the model actually attends to a different person that's mentioned later on in the input. And in terms of the results on the experiments, I think PhD, which is the model they built, it performs surprisingly well, given that it's trained directly on these raw images. And as a counterpoint here, I'm showing you the performance of BERT model trained with manually transcribed text instead of having to work directly with raw pixels. So I think that there is a real opportunity to work with historical document collections without having to annotate everything and transcribe everything in the dataset. So what I've tried to show here in this last part of the talk is how we can readily adapt this pixel framework to work with historical documents, in this case, scanned text. And we can also see, and I haven't spoken about this, that it seems to learn a semantically meaningful embedding space when we embed newspaper clippings and we do a nearest neighbor search in the encoding space. Maybe the slides will be available afterwards and you can look at these examples in more detail. I want to finish off here now with some final words. I believe that the time is good. So for me, the big question here is, why does this work? So masked language modeling is just classic distributional semantics, where you take a word or a couple of words within a sequence, you mask it, and you try to predict the distribution of words in a surrounding context. This is something we've known for a really long time. Pixel does this at the pixel level. It doesn't know anything explicit about those words. It just tries to reconstruct using a mean squared error objective. So why is it possible to learn a good encoder just by predicting these masked pixels? I don't yet know the answer, and if you think you do, please come and speak to me after. I would love to have a better theoretical justification for why this should work. You can also try this yourself. If you have a mobile phone, this is for reconstructing pixels. All of our code and all of our models are publicly available online. All of our documentation is online as well. This model is pre-trained on English text. If you copy and paste Polish text into it, it will not produce the best Polish reconstructions. It doesn't know anything about the special characters that are used in the Polish language, for example. But if you take English text from maybe a newspaper that published an article today, it should do a reasonable job of doing these reconstructions. And there are also some reconstructions that you can just play with immediately within the app yourself. In terms of ongoing work, we're nowhere near finished here. We're trying to work on multilingual pre-training so that I don't need to say things like, this won't be good for reconstructing Polish text. We're trying to work on a careful balance between how much data we need to observe and writing scripts. And we also want to avoid the model learning script-based representations, which is something that was shown, that will be shown in a paper to appear in December this year, where the cluster embedding here shows that a pixel-based translation model learns really distinct spaces for different writing systems, which is a bit suboptimal in multilingual learning from a pre-training perspective. We're also trying to advance this towards pixel encodings for producing words as outputs. For example, maybe using hybrid encoders that work over pixels and tokens, or maybe some kind of OCR reconstruction instead of just pixel reconstruction. And we're also trying to figure out what type of data matters. We're running experiments where maybe we pre-train on images where there's no linguistic grammar, all the way up to natural language, which has a complex linguistic grammar. One of the things we found is that it really matters, but you can get quite far if you pre-train on code and you include documentation strings. There is a really useful purpose of documenting your code when you're uploading it to GitHub. So please continue to do that. It's very important for us to learn language representations from something that's not Wikipedia. I'm going to finish here. I've tried to argue today that Pixel is a new type of language model that tackles the open vocabulary problem using visually rendered text instead of tokens. This enables high-quality transfer to unseen scripts. It also has robustness to orthographic attacks and code switching. I haven't shown code switching in this talk, but it's in some of our articles. And I think it's also a natural interface to working with scanned and historical documents. I want to finish by thanking the Willem Foundation in Denmark for supporting this research. And as a shameless plug, I am hiring PhD students to work in these areas. The deadline for applying is November 15th. If you are interested, please come and speak to me at some point during the conference. Thank you.